Okay, so recording has started. So I'm going to share my screen with you. So this is the web page that you should all be able to see once you go to Blackboard and you click on that link. Okay, so today's lab is lab number 1. Our course is physics 204. The first lab is sound. So I'm going to click on that. And these are the instructions. Okay. So basically, we are going to study the speed of sound. Okay. Sound has a finite speed. Okay. So it takes time for sound to travel. Who has any idea what the speed of sound in air is approximately?
Is it like the speed of light?
Not quite. Actually, not at all. Not at all.
Is it around 300?
300 what? What units?
Milliseconds?
Nobody knows. So sound approximately travels about
343.
343, but what units?
Meters per second.
Meters per second, SI units. So that's about, so if sound crosses about 3 football fields, 3.5 football fields every second. Okay. That seems to be fast, right? How about light? How fast does light travel?
Is it 3 times 10 to the 8th meters per second?
Okay. How big is that compared to the speed of sound?
It's really big.
But yes, but 2 times bigger, 5 times bigger.
I'll say, roughly like by 8 times bigger.
8
7, 8
times
times.
bigger.
Yeah, I'm not sure.
Does anybody else have any idea how bigger the speed of light is compared to the speed of sound? But so the speed of light is 3 times 10 to the 8th meters per second. Okay, so that's 300 million meters per second. 300 million meters per second, while the speed of sound is about 3 times 10 to the second meters per second, or 343 meters per second. Somebody has a suggestion in the chat room, I think. Or 900,000 times bigger. Yeah, about 1 million times bigger. So light travels about 1 million times faster than sound. Yes, absolutely. Okay, so light is very, very fast. Okay, it's very fast, but it's not instantaneous. Okay, it's not instantaneous, meaning that when you look at somebody who is standing right next to you, or who's facing you, even though they are standing 6 feet away from you, you are not seeing them as they are now. You are seeing them always in the past. Okay, maybe a few nanoseconds ago, but always in the past. When you look at the sun, when you look at the moon, for example, at night, you see it as it was in the past. You don't see it as it is now. In the past, but when in the past? How long does it take light to travel from the moon to us? Does anybody have any idea?
Isn't it like light years? No.
Light years. Light years, that's a light year is not a unit of time. It's a unit of distance. Saying light years is the same thing as saying miles or kilometers or feet or inches. Okay, it's a unit of distance. It's not a unit of time. Okay, a light. What is a light year? Somebody must have an idea of what a light year is. You're science students, so I'm sure
What do
you're
you
very
mean?
curious.
Like, what do you mean what a light year is?
Yeah, how would you define a light year? If somebody asked you, what is a light year? You know, I saw what are popular science fiction movies, Star Trek, Star Wars, and they talked about light years. What does that mean? How would you answer that question?
Like 6 trillion miles.
6 trillion miles. Possibly, I don't know. 6 trillion, it's a measure, it's a distance. Yeah. It could be the distance that light travels. That's a very good answer. So so Deborah says the distance that light travels in a year, in 1 year. Okay, so that's what a light year is by definition. If light travels 300 million kilometers every second. No. Is that 300 million? Okay. No, 300 million meters every second, which is the same as 300,000 kilometers every second. Then you have to multiply by how many seconds there are in a year to get the distance in that light travels in a year. Okay. All right, so it's a distance. It's a very, very long distance. Okay. So you can't answer the question how long light travels from the moon to us in light years. That's not the appropriate units. The units must be seconds or minutes or hours, units of time. Light year is not a unit of time, it's a unit of distance. So who has an idea? How long does it take light to travel from the moon to us? Just any guess. No, it's just a guess. We're students, so any answer is fine. 1 second. That's correct. That's actually correct. It takes 1 second, 1.3 seconds for light to travel from the moon to us. About 1.3 seconds, because the moon is not always the same distance away from us, but approximately on average 1.3 seconds. Okay, so we always see the moon as it was 1.3 seconds ago, never as it is now. Okay, how about the sun? It's still daylight outside, still daylight. So if you go out and see the sun, how long did the light coming from it take to get to us? 9 minutes. So cartoon says it says 9 minutes. Momena cartoon. That's approximately right. That's approximately right. It takes 8 minutes for the light from the sun to get to us. So when we see the sun in the sky, we see it as it was 8 minutes ago, not as it is now. Okay, we can never see it as it is now. Okay, and
20 seconds.
Actually, 8 minutes. 8 minutes. So we see the sun as it was 8 minutes ago. Okay. So if the sun was to disappear or explode, we wouldn't know about it for another 8 minutes. So how about the stars? How long does it take light from the stars to get to us? Any idea? Let's say the nearest star.
4 years.
About 8. The nearest star is about 8 years. 8 years. Okay. But most stars are much farther away than that, of course. Okay. For some of them, it takes 1,000 years. Yes, we are seeing the past. When you look at the sky, you see the past. You never see the stars as they are now. You see them as they were a long, long time ago. Very often, thousands of years ago, millions of years ago. Many of them are probably dead by now. Yeah, so if we travel far enough from Earth, we can see into the past. But the problem is you can never travel faster than light. Okay, you can. There is a limitation on the speed at which we can travel, and as a matter of fact, for a massive object like us to travel, it is impossible to even reach the speed of light. Okay, so we can't get to the speed of light, but we can see the past. Definitely, we can definitely see the past, and we see it all the time when we point telescopes at the sky. Okay, and we see the stars as they were in the past. Okay. Yes, this comes from Einstein's theory of relativity. He's the very first one to have figured that out. Okay, that we cannot travel at the speed of light. Okay. Yes. But the fact that when we look at the stars, we see the past. This was known even before Einstein. Okay, it was known when the speed of light was measured for the first time, a few hundred years ago. Okay, the Andromeda galaxy, for example, which is the nearest galaxy to ours, to the Milky Way, is, if I remember, 2.5 million years, million light years away from us, which means that we see it as it was 2.5 million years ago, not as it is now. Okay, but today we are interested in the speed of sound, not the speed of light. Okay, and you are given a few examples in the introduction. For example, when you see lightning, okay, you don't hear the thunder until much later. Why? Because lightning, you see it because it's light that's traveling, that's getting to your eyes. But the thunder, it's the sound that gets to your ears, and it has to wait longer, okay, much longer. So you hear the sound long after you have seen the lightning. Okay.
So, Professor, that is why, like, we see like the light of the thunder before we hear the sound of the thunder itself.
Absolutely, absolutely, absolutely. That's why we see the light of the thunder before we see the thunder itself. Okay. And if you watch the news, okay, many places around the world are in are war zones. Okay. And the journalists very often comment that they can see the explosions of bombs before they hear the sound of them, of the explosions. And that makes perfect sense because it takes light a shorter amount of time to travel than it takes sound. Okay. So in this lab, we are going to measure the speed of sound. Now that's a very good question. So why is it that we see people talking and hear the words at the same time? Well, it's because they are standing very close to us. Okay. Typically, they stand very close to us. Okay. Even if somebody is standing so 100 yards away from you, or yeah, about 100 yards, which is quite far, right? The light travel, the time it takes light to travel to you, and the time it takes the sound of their voice to travel to you, that time is so short that our brains are not able to distinguish between the two. Okay, so that's why we see them speak and hear them speak at the same time, basically, because the distances that people are away from us are so short that the time it takes the light to get to us and the sound they make to get to us is very short. So our brains cannot distinguish between the two. Yeah. So yes, that's crazy, but that's the world of physics. Everything in physics is unusual, unexpected, and fascinating. Okay, so now our lab, so which is sound. So I need to click to the first. Okay, where is it? First link. Okay, the first link is here, so I click on it. Can you see my screen? Can you see the simulation, my simulation?
Yeah.
Yeah, we can see it.
Okay, you can see it. Good, good. So I'm going to follow the instructions. Okay. So if I hit begin, I hear an explosion. Okay, it's a charge. It's some dynamite that's exploding. Okay. Now, so the dynamite or whatever charge we are talking about is this black dot. Okay, it's the black dot, and our position is the X at the bottom. See that? We are standing at X, and the charge or the dynamite or whatever we are using in our experiment is the dot. Okay, so we are told that we can move the dot by clicking on move. Can you see the chat, the chat room on my screen, or you cannot see it?
We can't see it.
You cannot see it. Okay. Okay. Because if you can, then I have to remove it so that it doesn't appear in the video. Don't want it to appear in the video. Okay. So to move the dynamite, you click on move. Okay. Unfortunately, it's very hard to control where it goes. But at the beginning, we are told to move it to 500 meters. 500, is it 500 meters? I think it's 500 meters. Yeah, but don't worry about that. Okay, move it wherever at the beginning. Okay, So mine is at 700 meters, okay? And then we are told to push on start. So I pushed on start, okay? And then if you wanna go back and make a change, you click on placement and you go back, okay? And then to come back to the environment where you were, you click on start. And to change the environment, you click on the environment. Here we are in a hot desert. If you click on the environment, you change to a cool desert, so a lower temperature desert. If you click on it again, you arrive at a frozen tundra. Click on it and you go back to a hot desert. So we're going to start our experiment in a hot desert, okay? So what do we need to do? We need, okay, let's see. I think to push on the detonator, okay? To push on the detonator handle so that our dynamite explodes, okay? And it will take time. It's going to explode, of course, but we will see the explosion almost right away. But because it's so close, we can say right away, but we will hear the sound only later because sound is slower than light. Okay, so we will see the explosion. I mean, here on the screen, I don't even think you will see it. You will just see the dynamite disappear, but you will hear the sound after some time. So let's get started. And then you have to stop the stopwatch to measure the time it takes for the sound to arrive at you. So push on the detonator, it explodes, and I press stop after hearing the sound. Okay? So that's 2,805 milliseconds. It took 2,805 milliseconds for the sound to arrive at me when the dynamite was sitting at a position of 700 meters away from me. Okay, and then you have to do this 3 times by pressing on reset and pushing on the detonator again. So I push, wait, hear the sound, press stop, and I get 2,679 milliseconds, which is the same as 2.679 seconds. Yes, that's 2.6 seconds, 2.6, 2.7 seconds. Okay, so you're supposed to do this 3 times and then make an average. All right, and then after you've done this for this first part of the experiment, you're supposed to go back and change the position of the charge. So you click on move and put it wherever you want. So here it randomly chose the distance 3.8 kilometers away from me. Okay, 3.8 kilometers away from me. And then click on start, and you keep the same environment. You do not change the environment for this first part of the lab. Okay, it has to be a hot desert. Then you press on the detonator, and you wait. Here, you press stop after you hear the sound of the explosion. So that's 11,352 milliseconds, or about 11.3 seconds. Okay, and you record that in the table. Okay, and you're supposed to do that and the distance, of course, which for me was 3.8 kilometers. Okay, and then you do this over 3 times, and then you make an average. You get it? And then Go to placement. Oh, somebody asked, what does the environment do to the sound? Well, it has a very big impact, and we will see that in the next part, part 2 or part 2, yes, part 2 and part 3. Okay, I think there's no part 3. Okay, we'll see that. So the question is, what does the environment do to the sound? Well, we will see that in part 2. Okay. Okay. Let me see. Somebody said, somebody asked a question. How many distances do you? How many? You want us to record, and you want us to convert milliseconds to seconds? Yes. So how many distances? For the first part, it is 7, I believe. 1, 2, 3, 4, 5, 6, 7. Yes, you have to change the distance 7 times for the first part, and then you have to. The question was, do you want us to convert milliseconds to seconds? Yes. Put your answers in seconds. Okay. In seconds, your time. I want the time in seconds, and the distance. How do I want the distance? The distance. The
Jeffrey
distance.
say divide by 1,000.
Yeah. To get from milliseconds to seconds, you have to divide by 1,000. So 1,000 milliseconds are equal to 1 second. Okay, 1,000 milliseconds is the same as 1 second.
Oh, okay.
And for distance, work in meters or kilometers. Do not work in miles or feet. Those are not scientific units. Okay, scientific units are metric units. Okay, meters, kilometers, and multiples of 10. Of them. So work in meters and kilometers. Okay, for distance, and for time, work in seconds. And then somebody asked, I think speed of sound varies based on climate. Yes, it does. The speed of sound depends on the climate. As a matter of fact, it depends on the temperature, and we will see that. Okay. Yes, it does say that in the lab manual. Okay. And then do we follow the lab manual? The lab manual, yeah, I mean, the link that I just clicked on. Yes, the link that I clicked on, so which is on Blackboard. Okay, go to Blackboard, you will see all the instructions. So follow all the instructions in the link. So I guess that's what you mean by lab manual. Okay, I guess that's what you mean. So if there are, yes, somebody asked, do we record these measurements 3 times for 3 different times and make an average? Yes, that's what you are told to do. Okay, so you have to do it 3 times for the same distance, and then make an average. Okay, for the same distance, and you will have to do that 7 times. So basically, you will need 21 measurements, 7 times 3. Okay, and 7 averages. 7 in total. Yes, 3 trials for each distance, and find the average of each. Yes, you can choose any distance. Definitely, you can choose any distance. What do you mean by location? Do you mean environment? Yeah, same environment. Yes, same environment. So hot desert. For part one, it must be the same hot desert. Okay, hot desert. All right. So now, after you do that, the next thing is to plot your results. You're going to plot a graph of distance versus time, okay, the average time it took the sound to get to you. The distance, so we want to study the dependence of distance on time. We want to know how the distance depends on time, okay? So in order to do that, you need an Excel file. So I have to help you, you can watch my YouTube video that's on my YouTube channel called Lab 1 Measurements, okay? To see how to do that in Excel, okay? It starts at, so the part that interests you starts at 17 minutes and 50 seconds, okay? So you should write that down. Lab 1 measurements, 17 minutes and 50 seconds. Or I can show you quickly. Let me see if we have time. Yeah, we have time. So let me see if maybe we can do that in 5 minutes. Let me open an Excel file first. Yes, to make a table. To make a table, you will see. So you have to check my video, Lab 1 measurements. But I'm going to show you here how you can do that. Okay. So let's say you want to study. Okay, what can you study? Hours studied, okay, and per week, okay, and GPA, okay. You want to study the relationship between these two variables. How the GPA depends on the number of hours studied. So you take a sample of 1,000 students, but here we are going to take maybe 10 students, okay? And you ask them, what's your GPA? And how many hours do you study on average every week?
Professor, we can't see the Excel sheet that you're working on.
Oh, of course you can't. Of course you can't. So let me go to it. Can you see it now?
Yep.
Okay. So GPA and hours studied. Okay. All right. So one of them tells you my GPA is 2.5. How many hours did I study per week? Maybe 20 hours. Okay, it's possible. Or maybe let's say 15 hours. Another one tells you my GPA is 1.8. How many hours did you study? Do you study a week? About 10 hours, if possible. Another one tells you 3.2. How many hours do you study per week? He says 27 hours. Another one says my GPA is 3.6. How many hours do you study a week? 45 hours. Okay. Another one tells you his or her GPA is, I don't know, 1.0. How many hours do they study a week? Maybe 12 hours. Another one tells you his or her GPA is 3.9. How many hours per week? 50 hours. Okay. Another one tells you his GPA is 0.5. How many hours a week? 6 hours. It's possible. How many do I have? 1, 2, 3, 4, 5, 6, 7. Another 2. Another 3. Another one tells you their GPA is 2.4. How many hours? 30 hours. Okay. Another one tells you the GPA is, I don't know, 3.0. How many hours? 32 hours. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. One last one. 0.2 GPA. How many hours do they study? 5 hours. Okay. So this is your survey. 0.5 50 hours a week, that's not possible. Okay, and then you want to study the relationship between these two variables. So what you do, okay, you select the title, you select all of this, okay, and then you go to insert, okay, insert. So in charts, you see chart. I'm going to choose the scatter plot. I choose the scatter plot. And this is what I get. Okay. Okay, I see. I'm going to change this a bit. I'm going to change this. I want our study to be the X variable. Okay. This makes more sense. Because you see, GPA is the dependent variable and our study is the independent variable. The GPA depends, we suppose, we guess, we think that the GPA depends on the hour studied and not the other way around. Okay. Okay, so insert chart scatter plot, and I get it. So the GPA depends on the hour studied in an almost linear way. Okay, not quite, but almost linear way. Okay, which means that all these points almost lie on a line or close to a straight line. Okay. Now, if you want to know that line in the equation of that line, you click in the chart, right click, okay, right click, and choose the option Add Trend Line. Click on it, okay, and choose linear. Choose linear. And then you may want to set the intercept. You don't have to. I maybe recommend that you don't in this case. In this case, you could, because obviously, if the student doesn't study out, maybe they can still get a non-zero GPA. Well, okay. don't worry about those. Set the intercept. Set the intercept means for number of hours equals 0, what's the GPA? What do you want the GPA to be? Okay, so don't worry about this. Display equation on the chart. You wanna check that. Display R squared value on chart. You wanna check that. Okay, and here is our equation. Can you all see the equation of the straight line? We call this straight line the regression line, or the line of best fit. Okay, the line of best fit, or the regression line, or it has many other names. Those are the two that I can remember. Can anybody read the equation of the line? If you can see it.
I got you, Professor.
But can you read it aloud?
Yeah, I can read it. 0.0732x. I think that's a plus 0.5123.
Okay, and what's R squared?
R squared is 0.8242.
Okay. So let's understand this equation. Okay. So basically, this is what you're supposed to do in point 4 of part 1. Okay. Point 4 in part 1. But so let me interpret this for you, and then when you do this for distance and time in the simulation on sound, you will give a similar interpretation, but based on the interpretation that I'm going to give to you for this example. Now, y is the vertical axis, which is the GPA for us. Okay, it's the GPA. X is the horizontal axis, which is the number of hours studied, the student studied, number of hours. Okay. Now, 0.0732 is the slope of the straight line. Okay. 0.5123 is the y-intercept, the intercept. Okay. Now, let's start with the intercept. I think that's the easiest one to interpret. So what it says is that if the students does not study at all, so studied 0 hour, their GPA will be 0.5123. The GPA will be the intercept, 0.5123. Okay. Now what about the slope? Okay. The slope says that if the student adds 1 hour to his or her study time, their GPA will increase by 0.0732. Okay? The GPA will increase by the value of the slope. So that's the interpretation of the slope. Okay? But for the case of distance of the charge or of the dynamite against the time it takes for the sound of the explosion to get to you, the slope has a special meaning. Okay, because I'm pretty sure you've seen this in your previous physics course. In uniform motion. Okay, what is the equation that relates distance and time? Can anybody tell us?
Velocity equals distance over time.
Yes, that's correct. Velocity equals distance over time, or another way to say it is distance equals velocity times time. Okay, distance equals velocity times time. Therefore, if distance is y, time is x, velocity has to be the slope. We get it? Because it's important that I mention this to you, because they ask you to find the slope and to interpret it. Therefore, in the graph that you will plot, the slope will have the interpretation of speed. Which speed? The speed of sound. Okay? So the slope you will find will be the speed of sound. Okay. So r squared, you don't have to find the r squared, but if it's great if you give it to me, okay? Because it's also useful. R squared tells you,
The
we
strength.
call it the coefficient of determination, okay? It tells you how close your data points are to the line of best fit, okay? You see that these data points are spread out around the line of best fit, okay? Our line of best fit represents an average, okay? When all these data points are close to the line of best fit, the r squared, which is called the coefficient of determination, gets close to 1. When they are far away from it, r squared gets close to 0. Okay, so now since it's 0.8242, we can say that this regression analysis that we have performed, okay, this regression line explains the variation in the GPA, so the number of hours, explain the variation in the GPA linearly at 82%. Okay, 82%, 82.42%. Okay, when r squared is 1, so that means that all data points are on the straight line, and and therefore the straight line explains the variation at 100%. Okay. All right, but we don't need this for our lab. Okay, it's just to help you understand what you are doing. Okay, so that's it with part 1. Are there any questions before we start part 2?
So Professor, for our lab reports, right, you want us to include like the graph, right?
Of course.
Okay.
In Excel. Okay, so just the way I showed it to you, plot it, and then copy and paste it in your lab report. Okay, and include the axes, the labels. So let me show you if I remember how to do this. Page layout, I believe. Okay, let me click in the chart. I think it's page layout. Or maybe, oh, okay, right here, design rather.
Professor, I have a question.
Yeah.
For the y and x axis, is the distance supposed to be on the y axis and time supposed to be on x?
Yeah.
All right,
Yes.
cool. Thank you.
Absolutely. Absolutely.
I think it's
Yeah.
design and add chart element.
Add chart element, good. Good. All right, that's correct. Good. So design add chart element, okay? Design add chart element. So you see the axis. The first option is the axis. So primary horizontal. Okay. No. Axis titles. Okay, so the second option. Okay, primary horizontal. So click on it and type hours studied. Okay, good. And then for so design add chart elements, axis titles, primary vertical, type GPA. Okay, sorry, GPA. enter. You press enter and it goes there. And the title, you can even change the title. So add chart elements. So design, add chart elements.
The title's already there where it says GPA.
Yeah. Chart title, above chart, centered overlay, and so on. I'm gonna choose above chart, and I'm gonna type relationship between GPA and hours studied. Press enter, and you have your title. Okay. Okay, and then and that's it. That's all you need to do. Okay. All right. Any other question before we move on to the second part? No question? Okay. So part 2 now. We want to explore the speed of sound in different climates. Okay. So what you have to do, so basically here, what we are studying is the relationship between temperature and speed of sound.
Professor, Shannon has a, he said, should we round to the 10th place or 100th place for the distance?
I want 3 decimal places. 3 decimal places.
Thank you.
Yeah. Okay. Now so the second part, speed of sound in different climates. Basically, we want to study the relationship between temperature and speed of sound. We want to know how the temperature affects the speed of sound. Does sound travel faster in colder weather, or does it travel more slowly? Okay. So to do that, we have another table, table 2. And so let me share my screen again with you. Okay. So you change the environment to cool desert, and then you do the experiment again. But now you have to choose one distance, okay? But a distance between 3 and 5 kilometers, okay? You pick a distance and you stick to it. You do not change it for all measurements, okay? For all time measurements, for all climates, all environments, okay? You do not change that distance, okay? And then you do this all over again. You press on the detonator and wait. With the explosion, press stop, and then record the time. Okay, and you do that 3 times for the cool desert. You do that 3 times for the hot desert, and you do that 3 times for the hot tundra. Okay, and you make averages each time, and then you at the end, what do you have to do? Well, you answer the questions. Well, you have to plot a graph of temperature versus time. Okay. Okay. So so that's what you have to do. you so at the end, you instead of plotting distance against time like we did in part 1, this time you will have to graph temperature against time, because these 3 environments have different temperatures. Okay. Now, and then the rest is questions that you have to answer based on the results that you will obtain. Yes, that's correct. Somebody is asking time on the x-axis and temperature on the y-axis. Yes. So we want time on the x-axis and the temperature on the y-axis. Okay, on the vertical axis.
Professor, what about the distance?
No,
like-
no distance, because the distance is the same for the last table. It's the same. So there is no dependence on distance. It's
Okay.
a constant. It's just temperature and time that you will need. Okay. Are there any questions? All right, so let me stop the recording, and I
I
will
have a
let
question.
you.
Oh, sorry.
You have a question? Somebody has a question?
Yeah, I have a question. About the lab write-up. Do we have to follow like the specific like format that's on the website where we find the simulations and the links? to
There's a
that?
special format there.
Like I remember last semester there was like a specific like introduction and like there's like a breakdown of how to do it. Like, do you want us to do it a particular way?
No, you don't have to do that, because I mean we are not conducting actual experiments. We are using just simulations, and that format was designed for actual experiments. So it wouldn't make much sense to me to follow that. Okay, it wouldn't make much sense.
Okay.
Just answer the questions that you find in the instruction file. That would be enough.
Okay.
Cynthia,
Thank you.
I have another question. So we just answered the questions and we don't have to like put an intro, procedure, nor conclusion.
Yeah,
Or
you don't need that. You don't need that.
Okay, thank you.
Professor, I have a question.
Yeah.
About table 2, right? Shouldn't temperature be on the x-axis and time be on the y?
No, the other way around.
Other way around? Okay.
Yeah. Yeah, you have to include both table, graph, and then the answers to the questions. Okay. Okay, so let me stop recording.
You want us to copy the questions or like as well into the report as well, right?
What matters is that you write down your lab report so that I don't get confused when I read it, so that I see clearly that you are answering the questions that were asked to you. Okay, so if you want to reproduce the questions, write them down or copy and paste them, that's perfectly fine with me. Okay, but what matters is that everything is clear to me, that I don't get confused by your answers.
Okay, no problem. Thank you.
Oh, sorry. Yeah, that's a good intervention here. Yeah. So Okay. So somebody is saying, shouldn't we have time on the vertical axis and temperature on the horizontal axis? If you want, you can do that. Okay, if you want, you can do that, because so what they're saying is, you can do that if you want to. Okay, you can have temperature on the vertical axis and time on the horizontal, or the other way around. That's perfectly fine. Okay, that's perfectly fine. The graph will look the same, and either way it will look the same.
Professor, you want us to include the tables as well, right?
Yeah, tables and graphs.
Okay.
Yeah. Okay, so let me stop recording because you don't need this in the video.